Hello, welcome to Applied Physics. This course is designed as per the R22 regulations of the JNTU Hyderabad. My name is Sharma. In this video, we'll start with the first unit of the syllabus, that is quantum mechanics, with an introduction to quantum physics. These are some of the great physicists who have made significant contribution in the early days of the quantum mechanics development. Niels Bohr, Albert Einstein, Max Planck, Pauli, Heisenberg, and Schrödinger. In your previous classes, you might have learned various aspects of physics, such as Kepler's laws of planetary motion, Newton's laws, other aspects of physics. In all such cases, we have dealt with macroscopic objects. Means those objects that are massive and considerably big in size. When you try to study the physics of molecules, atoms, protons, electrons, and other elementary particles, then one encounters new aspects of nature. These new aspects of nature are generally referred to as quantum phenomena. And a study of these quantum phenomena is called quantum physics. Means when one tries to study the behavior of molecules, atoms, protons, electrons, and other elementary particles, new aspects of nature will be encountered. These new aspects of nature are generally referred to as quantum phenomenon, and a study of these quantum phenomena is called as quantum physics. A mathematical theory of quantum physics is called quantum mechanics. Essentially, the quantum mechanics is a mathematical theory of the quantum physics. The laws of quantum physics are general laws of the nature. This is another important feature of quantum physics. The laws of quantum physics are the general laws of the nature. Now we'll try to understand the limitation of the classical physics. Means the area in which the classical physics fails to explain. To understand this, we'll recollect an aspect of physics, that is relativity. In relativity, If you remember, a problem is said to be a relativistic problem if the velocity of the object is comparable to the c, that is, c is the speed of light. Means if the velocity of the object is comparable with c, that is speed of light, then the problem becomes a relativistic problem. Then it becomes a relativistic problem. Otherwise, it is a non-relativistic problem. Which means speed of light c is the criteria to decide whether a problem is relativistic or non-relativistic, because we are using speed of light as a criteria to decide or to call a problem as a relativistic problem or a non-relativistic problem. A similar constant exists in quantum mechanics called as the Planck's constant. That is represented using a h whose value is 6.625 into 10 power minus 34 joule second. Please note that it is joule second but not joule per second. Dimensions of the constant are energy times time, that is equal to length times momentum, that is equal to the angular momentum and which is nothing but the action in physics. So the dimensions of the Planck's constant are the dimensions of the action are energy times time, length times momentum. What is length times momentum? If r is the radial vector and p is the momentum, then r cross p, length times momentum, gives us the angular momentum L. So the angular momentum is nothing but moment of the momentum. So the dimension of the Planck's constant are energy times time, length times momentum, or the angular momentum, or it is the action. So if you have a problem on hand whose dimensions are equal to h, r that of the h, and whose value is comparable with h, then the problem qualifies to be called as a quantum mechanical problem. otherwise not. This means if you have a problem on hand and whose dimensions are that of the Planck's constant h and whose value is comparable with h, then the problem becomes eligible to be called as quantum mechanical problem or quantum mechanics problem. Otherwise, it is not. In the early 20th century, blackbody radiation photoelectric effect and size and shape of atoms could not be explained using the physics that was known to them at the time. So they could not be explained by the physicists with the physics that was known to them at the time. Quantum mechanics provided a convincing, suitable explanation to these problems and many more other problems. That is why the quantum mechanics becomes relevant and plays an important role in the modern physics. We have started our discussion with the known physics. We have said that in the previous classes you have learned Kepler laws of planetary motion, Newton laws and other aspects of physics. And in all these cases, we have dealt with objects that are very, very huge or macroscopic objects. When one tries to study the molecules, atoms, protons, electrons and other elementary particles, one encounters new aspects of nature, and these new aspects of nature are generally referred to as quantum phenomenon, and a study of these quantum phenomena is called as quantum physics. A mathematical theory of quantum physics is called quantum mechanics, and the laws of quantum physics are general laws of the nature. We have seen the limitations of classical physics with the help of relativity. In relativity, if the velocity of an object is comparable with the c, that is speed of light, then the problem is said to be a relativistic problem. Otherwise, it is a non-relativistic problem. So here, speed of light is the criteria to decide whether a problem is relativistic or non-relativistic problem. A similar constant exists in quantum physics. It is known as Planck's constant, h, whose value is 6.625 into 10 power minus 34 joule second. Dimensions of h are energy times time, length times momentum, angular momentum, or it is the action. If you have a problem whose dimensions are equal to h, whose value is comparable with h, then the problem qualifies to be called as a quantum mechanics problem. Otherwise, it is not. In the early 20th century, blackbody radiation, photoelectric effect, size and shape of the atoms could not be explained with the physics that was known to the physicists at the time. Quantum mechanics provided suitable, convincing explanation for blackbody radiation, photoelectric effect, size and shape of the atoms, and many more other problems of physics. That is why quantum mechanics plays an important role in the modern physics. Thank you.